Now, let us recap what we have learnt in this course. Introduction to Structural Design. Structural Engineering. Structural engineering is a civil engineering branch focused on designing, analyzing, and constructing structures to ensure their stability, strength, rigidity, and safety. Structural engineers are essentially responsible for the bones and muscles of structures like buildings and bridges, making sure they can withstand various forces, gravity, wind, earthquakes, throughout their lifespan. They use mathematics, physics, and material science to calculate how structures will behave, selecting appropriate materials and geometries. Their main goal is safety and durability, ensuring structures are safe for use, won't collapse, and will perform reliably over time, adhering to building codes. Structural engineers are problem solvers who optimize material use and stay within budget. They collaborate with architects and contractors to integrate designs. Their work spans a wide range of structures, from homes to complex bridges and industrial facilities, making them crucial for the safety and functionality of our built environment. Engineering codes are sets of rules and regulations that govern the design, construction, and use of engineered systems, products, and structures. They act as minimum requirements and guidelines to ensure safety, quality, reliability, and consistency. Key points. Legally enforceable. Many codes are adopted by governments, making compliance mandatory. Expert developed. They are created through consensus by professional organizations and experts, incorporating best practices and lessons from past failures. Safety first. Their primary purpose is to protect public health and safety by minimizing risks of failure and accidents. Quality assurance. They set benchmarks for consistent quality across projects. Consistency. They provide a common framework for engineers globally. Regulatory compliance. They help meet legal requirements and obtain necessary approvals. Foundation for innovation. While setting minimums, they provide a reliable base for new solutions. Examples include the International Building Code, IBC, and standards from organizations like ASCE and ASME. In essence, they are crucial for the integrity, safety, and performance of all engineered constructions. Structural design. Structural design in civil engineering is the process of analyzing, designing, and constructing the frameworks of buildings and other civil structures. Its main goal is to ensure these structures are safe, stable, durable, and functional. This involves analyzing loads, dead, live, environmental, dynamic, the structure will face. Selecting appropriate materials like concrete, steel, or timber. Designing and sizing elements such as foundations, beams, columns, and slabs. Ensuring key principles like stability, strength, stiffness, durability, and economy are met. Collaborating with architects and adhering to building codes. Essentially, structural design builds the safe and strong backbone of any construction project. Codes of practice. Structural engineers use various engineering codes and standards, depending on the project's location and type, to ensure safety, efficiency, and durability. Key categories of codes include general building codes, like the International Building Code, IBC, US and International, and Eurocodes, Europe, which provide comprehensive regulations for overall building design. Many countries also have their own national building codes. Load design standards, such as ASCE SEI 7, US, which specify minimum design loads, dead, live, wind, seismic, snow, a structure must resist. Eurocode 1 serves a similar function in Europe. Material-specific design codes, these detail design requirements for particular materials. ACI 318 for structural concrete. AISC 360 and AISC 341 for structural steel. NDS for wood construction. Bridge design codes. AASHTO LRFD bridge design specifications, US, are primary for highway bridges, with specific Eurocodes used in Europe. Other relevant codes include those for seismic evaluation, ASCE SEI 41, welding, AWSD 1.1, and fire protection, NFPA codes. Structural engineers must stay current with these codes and any local amendments, as they are crucial for compliant and safe structural design. Structural loads. Structural loads are forces, deformations, or accelerations applied to a structure, crucial for ensuring its safety and stability during design. They cause stress and deformation within structural components. The main types of structural loads are dead loads, permanent constant forces from the self-weight of structural elements, beams, columns, walls, and fixed fixtures, plasterboard, fixed machinery. Live loads, variable changing forces due to occupancy and use, such as the weight of people, furniture, movable equipment, or vehicles. Environmental loads, forces from natural phenomena. Wind loads, pressure and suction from wind. Snow loads, weight of accumulated snow on roofs. Seismic loads, forces from earthquake ground motion. Rain ponding loads, weight of accumulated rainwater. Thermal loads, forces from material expansion contraction due to temperature changes. Hydrostatic loads, pressure from water or fluids. Soil loads, lateral pressure from soil on retaining structures. Special accidental loads, less common but potentially significant, including impact loads, vehicles, machinery, blast loads, settlement loads, and fatigue loads from repetitive forces. Engineers analyze these loads and their combinations to design structural elements with adequate strength and stiffness to safely resist all expected forces. Structural elements. In civil engineering, structural elements are the fundamental components of a structure, like a building or bridge, that are designed to resist and transfer various types of loads. They form the skeleton that provides strength, stability, and shape. Key structural elements include foundations, transfer the structure's load to the ground. Columns, vertical members resisting downward, compressive, forces. Beams, horizontal members resisting bending and transferring loads to columns or walls. Slabs, flat, horizontal elements forming floors and roofs. Walls, both load-bearing and shear walls provide support and resist lateral forces. Trusses, frameworks of connected members efficient for spanning large distances. Bracing systems, provide lateral stability against forces like wind or earthquakes. Ties, members under tension, pulling forces. Struts, members under compression, pushing forces. These elements work together to ensure the safety, integrity, and functionality of the entire structure. The whole structural picture. Civil engineers achieve the whole structural picture in structural design by taking a holistic, integrated approach beyond just calculations. This involves understanding project context, integrating the architectural vision, analyzing site conditions, geotechnical, environmental, meeting client needs and budget, and adhering to local building codes and regulations. Holistic design process, comprehensively identifying all loads, dead, live, environmental, special, and understanding how they transfer through the structure, load paths. This includes selecting appropriate materials, using advanced analysis tools, like FEA, while applying sound engineering judgment, and detailing designs for constructability. Integration and lifecycle thinking, collaborating closely with other disciplines, architects, MEP engineers, managing risks by designing for redundancy and resilience, and considering the structure's long-term performance, maintenance, and sustainability throughout its entire life cycle. Ultimately, it's about blending technical expertise with practical understanding and collaboration to design structures that are safe, functional, and durable for generations. That brings us to the end of this module. You may now take the quiz and also complete the assignment. Thank you.